So you're right, the domain is all real numbers. Let me show you what that would look like if you wrote it. The cool little symbol for all real numbers. Whoa. Domain. It's like a layered R. All real numbers. Or the way I like to write it, negative infinity to positive infinity. Who can tell me the range of this function? Ollie. Yes. What is the range? Very good. Who can tell me what I need to put after the 2? Bracket. Very good. Anytime you deal with infinity, it's always be parentheses. But anytime a number is included in a set of numbers, you put a bracket. So there'll be a bracket there showing that negative 2 is also included. It doesn't just stop at negative 2. Oh, let's see. Part C. The x-intercepts, if any. Joe. Very good. None. It doesn't cross that stinking axis at all. No x-intercepts. Y-intercepts, if any. Sarah. Very good. Crosses right there. Negative 2. And let's see. Missing. Oh, right. These down here. Who can tell me what f of negative 4 is? Troyan. Nope, you're right. I just can't read. Negative 5. You're correct. And what is f of positive 4? Oh, we're on the last one. Somebody's got to volunteer. Other than Troyan, because she just did one. Kayla, what is f of positive 4? Positive 4. Very good. Negative 2. Negative 2. Raise your hand if there's a particular component of those that you would like, A, B, C, D, any of that stuff that you would like a little bit more explanation on. Domain is all. Yes, sir. Part B, the range. All right. The range are all the y values covered. Now, remember we just had coordinates. The range was just you listed the y values. Well, when you have a graph, you have to list all the y values it covers. So it's easy to just do it in a range. It just keeps going down. So that's negative infinity, but it only comes up to a negative 2. Whoa. I feel like the Joker. I just made it disappear. There we go. Is that your question? And a good question it would have been. Is this like really long here to anybody else? Anybody else? Any part? Any parts of this somebody would like to see at all? Great. That's good. On your DOMs. We're just going to put it on your DOMs. Flip your DOM over. Hopefully you don't have anything on the back. We haven't had any lengthy DOMs. If you do, that's fine. You can add something to a separate sheet of paper and attach it to your DOM if there's no room. On your DOMs, I want you... It's going to take like a lot of clicks. Actually, this is stupid. I'll just close this and reopen it. We are going to do 7 more like that on your own. As soon as you're done, you're going to turn it in. I know, exciting. Yay. So, they're going to be numbered up here, so just use the numbers on the problems. And this will be included in your DOM, and then you will turn it in. Here we go. We just did number 87, so obviously you can skip that one. I need you to do the other 7 on the board. I'm sorry, the directions can't get you bigger. However, this is out of 1.2 in your book, number 77. So if you need to see them a little closer, it is also in your book, if you'd like. I will come around and assist, and there's no point in me recording this. Find the intervals for which the function is increasing. Again, this is 1.3 if you're labeling your notes. This is 1.3, and that's what you're labeling your homework as later. On what intervals is this function, we'll look at number 1, increasing? Who thinks they can tell me where that thing's going uphill? Like it's a domain you're giving me. Where do you think it starts going uphill? -1, very good. And does it ever stop going uphill? No, the arrow implies it's just going to keep going. So part A for number 1, A, you can label it increasing if you want. I'm just going to label it A, would be -1 to infinity. Now a lot of people are like, if we're looking at the y values for going up and down, why do we label it as x values? Well, every graph, one of these SPIs, 2.2, interpreting functions to use a variety of Chuck Norrisy methods. Actually, that's not the one I was looking for. Oh, well, one of those. We'll find it in a bit. Oh, 2.4, use functions to solve problems, duh. These functions are going to start modeling real-life applications. And the x-axis is almost always in terms of time. So like this is how far you were from your house at a given time. So I might say, well, when you were 4 meters from your house, what time was it? This is just a raw example. You'd be like, oh, it's 2 p.m. So the x-axis is 98% of the time the one we're referencing when I ask you for any kind of interval or point or anything like that. What about decreasing? Where do you think it's going downhill? Feel free to volunteer so I don't have to call on somebody. Joey. -infinity to -1. Very good. In case you're wondering, at -1, like instantaneously, it's not decreasing or increasing, and at that exact moment, it's neither. That's why they don't have a bracket on them, because it's not increasing or decreasing. Which brings us to part C, intervals on which the function is constant. There's really no interval, but what's the one point that that's happening? -1. And it's the only, well, since, yeah, might as well. -1. If you put that in parentheses, that'd be fine too. It's only a point anyway. But, in fact, you really won't need those on any of these, so you can just use parentheses for all these. -1 is the only point where that thing is neither increasing nor decreasing and is therefore constant. The slide we did just a second ago, you know, I think it was the one we did in the DOM actually, which of course I've taken off the board. But you know that one that just went flat? That is an interval of constant. So I bet number 2 has one of those, but I've covered it up. Number 3, who thinks you can tell me the interval of increasing? Anybody? Where's that thing going uphill? Your voices. Like, you know, one of these would work too. Throwing it out there. Zach, what do you think? Where's that thing going uphill? You nailed it. Starting at 0 to infinity, it's just rising. What about part B? Where's that thing going downhill? Does this mean nowhere? All right. Nowhere or none or however you want to write that. It's not going downhill anywhere. Is it flatlining anywhere? No. Even at this exact spot, it's starting to go immediately uphill. So, none again. Questions about those two, about what we're looking for? Okay, moving on. Same thing, intervals of increasing, decreasing, and constant. We don't have to work all of these. I'll just pick one at 2, 3. I'll pick 2 of them at random. Number 9, increasing. This one has several different little intervals. Shelby, where do you think that thing's going uphill? Number 9, all of them. You can start on, oh, right, Emmons. This table's open if you'd like to scoot up for the day. Okay. You mean that's where it like stops increasing? Well, you're right. At 0, it stops increasing, but where does it start to the left of that? Negative infinity, yeah. This thing just keeps falling, but you remember, you read a graph like a book, left to right. So it looks like from negative infinity all the way up to 0, that thing's increasing. Now there's going to be 3 different intervals here. No, excuse me, 2. And here's another spot where it's going uphill. And what are those coordinates? Shelby, you just finish this one up. You're looking at the y's. Remember, we're looking at this in terms of, you're right in the fact that we're looking at where it's rising and falling in terms of y, but you're going to give it to me in intervals of x's. Yeah, well, it looks like 2, probably especially from back there. I think it's actually right in the middle, but I get that you thought. It's just kind of hard to see from back there. It's 1.5, or I'll just call it 3 halves to 3. It's going uphill. Before we go any further, are there questions about where those numbers are coming from? Because it's 1.5. I just wrote it as an improper fraction. Decreasing. Where's that thing going downhill? Savannah, bring forth your answer. Very good. I'll do it in mixed fraction notation this time. Where else is it going downhill? Actually, with the arrow, you just assume it keeps going. So, right. Nailed it. Good job. And what are the exact points where this thing isn't going anywhere? What are just the 3 coordinates? In fact, if you just want to label these as coordinates if they're just points. I'm sorry? Where does it turn from one of the others? 0, 1.5, and 3 are the exact spots. They're not intervals, they're just spots where it's neither increasing nor decreasing. Good. That was number 9. Let's look at number 11. That one looks fun. Number 11. Increasing. Who am I going to pick on? Corey. Where's that thing going uphill at? Does it stop increasing at this point, or does it just change the amount of which it's increasing? But it's still going up, right? So I'm just going to clump those together. Yeah. If you would put it as 2, I wouldn't have counted off. But just know that during a test, it's just going to label it as 1. So we're just going to put that as 1. Where's it going downhill? Nowhere. None. And where is it? Oh, you are off. I hope so. I'll be letting you know real soon, although that looks very, very scary.
I doubled it. I didn't cut it off, so you got 2 pieces now. Well, now, rip a hole in it.
Well, believe me, if I can, then the net's going to rip it like that. But I will.
But I think so. I think it's like 3 times.
If you're confident, I'm confident. Thank you. So I just found out, like 2 days for our first game, that this is the thing that tightens our net for the volleyball team, and it was like ripped 90%, which is really bad news. That's like, imagine the football team found out their goalposts were broken and they were like laying on the ground 2 days before a game. That's a problem. Well, same thing. So luckily she fixed it for me. It's awesome. Anyway, if you're watching at home, Miss Cunningham was just awesome just now. Okay. Intervals of constant. Where does that thing flatline? Morgan. I can't hear you. You're correct, but see, the arrow kind of implies it just keeps doing the same thing. So what would that actually be? Very good. To what? Very good. And is there another one? And it is? Nailed it. Good job. Questions about where we are getting these intervals, what we're looking at, where our numbers are coming from, any of that kind of stuff. Yes, sir. Okay. To be honest, in the past, I didn't really make people list these, but it's an important calculus concept that it's like when you throw a ball in the air. Going up, going up, going up, then it's coming down. Right at a very split second, when it's neither going up nor down, that ball freezes for a millisecond. It's neither going up nor down, therefore it has no speed. So same principle here. At that exact spot, it's neither increasing nor decreasing, therefore it is constant. That's just nothing. if you look at it in terms of speed, which I tend to do. Does that make more sense?
Number 11.
Oh, this one. Oh, yeah. You mean why they're infinity? Because the arrow implies that it just keeps going. So you think, well, if it, imagine you just kept drawing this, well, it'd be negative infinity all the way until negative 2.
Oh, I was looking at the wrong.
Oh, that is a common mistake. A lot of people make that mistake. Heck, I make that mistake sometimes. I think I did on Wednesday. Because I know I'm asking you about your y values, but I'm asking you to tell it to me. Yeah, that's something we're all going to struggle with together for a while. Any other questions about something? Yes, sir.
On the A of 11, how come we put positive 4 after negative 2 plus 4?
You read it left to right. So it starts at negative 2 and ends at 4.
But that's not like that.
You give me your answer. Oh, I see what you're thinking. Are you thinking that as like a coordinate? No, these are intervals. I know it's confusing because we use parentheses for both, but that is an interval. That is strictly x-axis spots. From x equals negative 2 to x equals 4. The important, it's probably confusing because I took away the directions, but whenever it asks you for an interval, it's going to look like coordinates, unless it has an infinity in there, but it's actually going to be an interval. Yeah. Does that answer your question? Other questions? Onward. Next slide. Okay, maximums and minimums. Let's go back for a second. You know how we said for number 9, at a split second, it's neither rising nor falling. Okay? Well, when a graph changes from falling to rising or rising to falling, we're said to have relative maximums and minimums, which I think is like mountains and valleys. Okay? If there is any specific part of a function where there is a lowest absolute point, then we call it a minimum, and if there's a top of a part of a graph, we call it a maximum. So, part A, the numbers, if any, at which f has a relative maximum. What are these relative maxima, which is apparently the plural for maximum? That wasn't bad. Who can tell me what you think a relative maximum will be for number 13? You can give it to me as a whole coordinate. Very good. There is a relative max. It's actually important you put relative, and I'll explain that in a minute, at 0, 4. Now, this is not an interval. This is a point. You're asking for points now. What about relative minimums? Sounds awesome. Any questions about where Joey got those? That was you, Joey, right? Good job. Any questions about where those points came from? The reason we call them relative is because imagine you had a function like this. It's just a straight up parabola. This point would be called the absolute minimum, which means on the entire graph, that is the absolute lowest point by itself. I don't know that we're going to deal with that too much. You're going to deal with it a lot in calculus, but so that's why it's good to state that these are relative. They're not the highest and lowest points in the whole graph. This is not the highest because the graph just keeps going. This is by far not the highest. And these are not the sole lowest because there's two of them. So neither of them is the lowest. So that's why it's important to get in the habit of calling those relative. What about number 15? Michael, that yawn tells me you know what you're doing. Go. Relative max. Kind of perfect. Why don't you go and just give me the min too? -1. Get that backwards. 1, -1. I do that all the time. Questions? Okay, moving on. Let me just tell you what's coming. Prepare yourself. That thing we started class with, we had to list 5 things. I believe it's this lesson where at the end you have those same things, but it's like A through L. There's like 12 things. So that's coming. Have fun with it. Okay. Determine whether each function is even, odd, or neither. I didn't remember this was today. Okay. There's an easy way and a hard way to do this. Okay. Easy way. An even function will have, the easiest way to do it is, does every single element in that function have an even exponent? Which of these do you think will be even? I can't hear you. 21. That's right. It will be even. They're both even. What else? 25. You're right. Because 23, couldn't you write this as x to the 0, which is also even? So you're right. 21, 23, and 25 are even. What about odd? Which one of these do you think might be odd? 17. And which one do you think will be neither? 19 and 27 are both neither. They both have one of each. Boom, boom. Now, what this means on a graph, you'll be thinking, who cares? Well, nifty noodle thing about these, any function that is even, an even function, you might want to put this in your notes because I can almost guarantee you this will be on a test. Even functions are symmetrical around the y-axis. Around the y-axis. Which means they will all look something, like that, where it could just, it's like a mirror image of itself. This would be another even function. These aren't perfectly drawn, but you get the gist of it. Odd functions. Here comes another piece of trivia for you. Odd functions are symmetrical with respect to the origin. What does that mean? Well, excuse me. Let me just pull up the calculator and show you what that will look like. Sorry, I'm going to get this out of your way in just a second. Let's graph an odd function on our calculator. How about x to the 5th minus x cubed? Odd, right? Graph. Let me zoom in. And the calculator I'm using here is the exact same kind I offer you guys, so all the things I do on here you're welcome to do yourself when doing your homework. Enter. Okay. Yes. Go. Alright. What it means to be symmetrical around the origin is that at every point, like here, directly on the other side of the origin, exact same distance and everything, there's a mirror point. So like here and here. Your fingers will kind of form a straight line. Here and here, directly on opposite sides of the origin. Here and here, here and here, here and here. Does that make sense? What I'm pointing at? Raise your hand if you're not seeing what my fingers are doing. It's like they're doing the exact same thing, but in opposite directions. Okay. Well, the big thing that you're going to need to know about this is, you know how I said A through L, you're going to have to do it? They're going to show you pictures of graphs, and it's going to say, are these even, odd, or neither? Easiest way to do that is to just look at it. If it's symmetrical about the y-axis, it's even. If it's symmetrical about the origin, something like this, then it is odd. And if it's neither, it's neither. Okay then. Mm-hmm. It's not symmetrical around the y-axis. No, symmetrical around the y-axis is going to look more like this. In fact, I'll tell you what, I'm going to put them right on top of each other so you can see the difference. X squared. Symmetrical around the y-axis means they have brothers like directly on the opposite side of justice, like going. That makes sense. I can't put the words very well. Yeah, good question. Other questions? All right. So just by looking, 29, even, odd, or neither. Blake. Very good. Very good. And 31, even, odd, or neither. Olivia. Very good. Very, very good. I could tell you why they bothered giving you these coordinates, but it's not very. I'm not going to bother right now. I might start class with it one day. It's really not relevant or helpful to what you're going to be doing with it. Okay, what did I say? A through L. Here comes the fun stuff. All right. We're going to knock this out all at once. I believe there's 2 of these. Perfect. Just enough for everybody in here to answer part 1. So, we're just going to make our way around and start in the back corner. Mr. Flowers, can you tell me the domain of number 33? Does it stop at 4 or does it keep going? Negative infinity, I didn't hear what you said second, but I'm going to hope it was, to positive infinity. This thing, there's no breaks in it. It goes every single x value. Or you could have put all reals, as we started class with. That would have also been a fine answer, all real numbers. If there's no breaks in it, and it has arrows, it'll always be everywhere. The range, how low and how high does this thing go? What am I called on today? I called on pretty much everybody. Except for Rachel. Wait, I thought we were going to start, whatever. Rachel, part B, go. That's exactly what it is. Very good. We're just going to keep going. If you have questions, just throw your hand up and we'll talk about it. X-intercepts, Denton. Very good. You could just write x equals 1, x equals 7. That'd be perfectly fine. I'm going to go ahead and write it as a coordinate. Y-intercepts, Karen. Very good. Y equals 4, or you can write 0.04. Either would work. Increasing. I'm going to start with the people I haven't called on today. And if I have called on you, I apologize, but just answer it anyway. Jessica, intervals of increasing. Where is it going? Uphill. I'm sorry? Remember, this is the same problem we had earlier. You're looking at the y's, but you tell it to me in terms of x values. At what x value does it start going uphill? 4. And where does it stop? It doesn't, so infinity. Decreasing. I think that's almost everybody. Haley, can you tell me where this thing's going downhill? From 0. Ah, good. I love kidders. Sabrina, where is this thing constant? Negative infinity to, remember, x value. There you go. Negative infinity to 0. Relative minimum. Melinda. Excellent. Yes, there would. And I totally missed it. There's a constant point at 4, or you can just put 4 in double brackets if you wanted to. Very good. Or parentheses, it doesn't really matter. But good catch. Relative minimum of f. Oh, okay. I know that seems redundant. Here's all this is saying. This one says the number at which f is minimum. So technically, I think all they wanted was 4. At 4, there's a minimum. And then when it says what is the minimum, that's where they want the whole coordinate. That's stupid. If you put the whole coordinate once, I don't work. you don't have to answer both parts. But that's the only reason it seems like it's repeating itself. J of -3. Man, I think I've called on everyone today. Except for, of course, Colton. Whoa, you lost him. Yep, very good. The values of x for which f of x is -2. Tricky. We only did one of these the other day. Let's see who can raise a hand and tell me. Yes, ma'am. -2. Very good. And because you stepped up to the plate, you can mark one of these off of your homework assignment. I think you have to do 3 or 4 of these. You can mark one off and say, stepped up to the plate. L, is this even, odd, or neither? Right. I haven't called on you either, but you stepped up too. Neither. No. So, I don't remember what this was. This was 2, right? X equals 2. So, this is neither. It is not symmetrical around either part. Questions? Oh, on G, that was a point for which it is neither decreasing nor increasing. Remember that was that ball example we talked about earlier? That is that one exact point where it's neither going uphill nor downhill. All right. Questions? All right. We don't have to do multiple of these. Let me just see if there's anything in this one that's not in the other one. Zeros. Zero is just zeros, roots, x-intercepts. They're all the same thing. So when you hear zeros, that basically means what are the x-intercepts. So I know you know how to find those and all like their intervals, values. Oh, this, part G. Who thinks they can tell me what that means? We've actually not done something like it. What does that mean? Yeah, exactly. Remember, when you're dealing with functions, f of x is basically another way to write y values. So this is saying, for what values of x are your y values less than or equal to 0, which is everything below or touching the x-axis, which would be what? Go ahead and finish it up for you. And because it's touching, it is equal, there'll be a bracket there. In fact, I'll just write this out. This would be negative infinity to -3 bracket, and what else? Remember, the equal sign is the key here. Where else does it equal 0? 3. Very good. That's a bracket. I just didn't do it very well. Good. Very nice. Are there any questions about where we came up with that? Like what he's talking about? Okay. Oh, see, we already did everything like that. Okay, here we go. We're done. Boom.